Just want to introduce Jean-Pierre, who, for whom I think interdisciplinarity has been kind of a natural thing since the beginning, because he started by the study of allosteric, the theory of allostery in enzymes, and then he did a lot of work on the brain, and during this time he had to draw from many disciplines actually, from physics to biology and chemistry. And in fact, the title of his talk today reflects this, and I think I would just ask him to start his presentation.
Merci.
Jean-Pierre.
J'ai fait les diapositives en anglais, je parle en français, est-ce que ça va?
Oui, très bien. Ouais.
Parce que je peux aussi parler en anglais, comme vous voulez. Enfin, je suis plus à l'aise pour ce genre de questions en français. Et je vais donc d'abord, je tiens à remercier notre président et nos invitants. Et je suis tout à fait d'accord avec ce qui vient d'être dit. Personnellement, je déteste le mot interdisciplinarité qui a été introduit dans ce colloque. Par contre, je suis tout à fait d'accord avec ce que tu viens de dire. Je crois que nous essayons tous de faire de la science et de progresser dans la connaissance du monde en général, qu'il soit celui de la physique ou celui des sciences du vivant. Je vais aujourd'hui essayer de voir avec vous comment ces divers techniques, à la fois sur le plan de l'instrumentation et surtout de la théorie, peuvent interagir pour essayer de comprendre un aspect majeur des fonctions du cerveau, la conscience, et montrer comment nous essayons d'envisager cette question plutôt que de vous apporter des réponses définitives, loin de là. Donc le but de ma présentation serait plutôt d'inciter les physiciens à s'intéresser à l'étude du vivant et aux neurobiologistes de poser des questions aux physiciens et de demander leur soutien et leur contribution pour essayer de résoudre un problème fondamental pour tout le monde, je pense pour le physicien comme pour le neurobiologiste, c'est comment fonctionne le cerveau du physicien. Ce n'est pas une plaisanterie, hein. Je pense que c'est un vrai problème épistémologique. J'ai essayé de débattre de cette question dans un livre qui s'appelle L'homme de vérité, où justement je me suis posé la question de l'apport éventuel des sciences du cerveau à la connaissance et à la connaissance scientifique en particulier. Et il se trouve que beaucoup de physiciens se situent dans une espèce de tour d'ivoire où ils examinent le monde, font des théories et ne se posent jamais la question de savoir comment leurs théories se développent dans leur cerveau. Et je pense que le statut de l'observateur en physique est un statut qui mérite un développement épistémologique qui, à mon avis, est très insuffisant de nos jours. Et il serait intéressant justement de se poser la question de savoir comment le cerveau, qui est un objet physique et qui est une machine physique, comment ce cerveau est capable de produire des théories sur le monde et de montrer leur adéquation, bien entendu du fait de l'évolution, au monde qui nous entoure. Donc je pense que le problème de l'observateur vu sous l'angle de la neuroscience est un problème central, je pense, de la physique d'aujourd'hui, et malheureusement n'est pas abordé par les physiciens qui persistent à avoir une espèce de vision idéaliste de l'observateur, et ils ne prennent jamais en compte dans leur propre théorie, ou du moins insuffisamment, sachant quand même tout l'apport de la neuroscience et des sciences cognitives récent à ce genre de questions. Donc je pense que c'est un problème d'avenir. Si j'avais un colloque à faire d'interface entre physique et biologie, c'est sur ce sujet-là que je ferais. Je n'ai pas dit du tout que je vais faire un colloque, hein, mais je pense que ça pourrait être un projet de colloque intéressant dans les années à venir. Et je pense qu'il y a beaucoup à dire dans ce domaine. Donc, ce qui nous préoccupera aujourd'hui, c'est la question de l'accès à la conscience, et d'une manière qui va relier entre eux des niveaux d'organisation bien différents. Et là, je voudrais souligner un point important, c'est que ce qui fait, à mon avis, la différence entre la physique et la biologie, les sciences du vivant, c'est que les physiciens s'intéressent en général à des objets relativement homogènes, et alors que les biologistes s'intéressent à des objets physiques extrêmement hétérogènes. Le passage, en fait, de ce qu'il est convenu d'appeler la physique et les sciences du vivant est parfois extrêmement difficile, et beaucoup de physiciens persistent à vouloir voir dans le cerveau un objet homogène, cohérent, et de le traiter sous, par exemple, tous les effets collectifs, etc., d'appliquer les lois de la physique qui ont été conçues pour des systèmes relativement homogènes à des objets fondamentalement hétérogènes, c'est-à-dire construits d'une toute autre manière, bien que ce soit aussi des objets physiques. Donc il y a beaucoup de pertes de temps dans les rapports entre physiciens et biologistes, entre autres de modélisation. Il existe des quantités de modélisateurs en physique qui font des choses qui sont très intéressantes, mais qui n'intéressent pas du tout le progrès de la connaissance en biologie. Je pense que le problème qui nous préoccupe, c'est de faire des modèles évidents qui soient susceptibles de faire progresser le savoir, la connaissance. C'est notre but, sinon on n'est pas des scientifiques. Donc, à cet égard, une meilleure connaissance de l'objet qui nous intéresse, que l'objet physique qui nous intéresse, qu'est le cerveau, à mon avis, mérite toute notre considération. Et donc, je vais dire quelques mots sur la modélisation du cerveau, quelques mots sur l'hypothèse que Stanislas Dehaene, moi-même et collègues avons développée, et puis peut-être, si j'ai le temps, essayer de montrer que nous avons essayé de travailler pour quand même une bonne cause, qui est la science expérimentale. Moi, je suis newtonien à cet égard. Je crois qu'il faut allier la théorie et l'expérience, et ne pas être cartésien, se passer son temps à faire de la théorie qui sert à rien. Donc, ou des expériences qui ne sont pas conçues pour résoudre un problème bien défini. Donc, ce sont des idées banales et simples, malheureusement triviales, mais qui sont pas toujours mises en application. Donc, évidemment, on peut se poser la question de savoir ce que c'est que la conscience, parce que si nous intéressons à une fonction du cerveau, encore faut-il savoir de quoi on parle. C'est un problème difficile, comme vous le savez, parce qu'il y a beaucoup de théologiens et de philosophes qui s'intéressent à la conscience et qui nous font perdre notre temps. Et il faut partir au départ d'une définition concrète, qui est celle d'un philosophe finlandais, pas français malheureusement, que la conscience c'est un phénomène réel, naturel, un processus biologique situé dans le cerveau, pas exclusivement dans le cerveau, parce qu'évidemment c'est le cerveau en interaction avec le monde extérieur. Je me permets d'ajouter ce point parce que c'est une remarque qui est toujours faite qu'on ne peut pas étudier la conscience sans l'environnement dans lequel se situe l'individu. Alors cette fonction s'est développée au cours de l'évolution à partir d'émotions primordiales. Je vous recommande un livre de Derek Denton qui est très intéressant sur la conscience, qui vient de sortir chez Flammarion. Et on ne peut pas dire que c'est un point important, contrairement à ce que dit Edelman, c'est pas simplement un accroissement de complexité. C'est un fait qu'il y a au cours de l'évolution des accroissements de complexité considérables qui sont produits, mais notre position, c'est qu'il y a des architectures spécialisées pour cette fonction, et que la conscience a été sélectionnée au cours de l'évolution, non pas à la suite d'un intelligent design, je crois qu'on est tous d'accord sur ce point, j'espère du moins, mais qu'il y avait des fonctions qui sont remplies par l'espace conscient, qui ont une valeur sélective, et donc il y a des architectures spécialisées qui se sont développées au cours de l'évolution, et que nous avons donc affaire à un espace de travail, un milieu conscient, qui n'est pas produit par l'interaction avec le monde extérieur, mais qui est modulé par cette interaction avec le monde extérieur. Et là, fait intervenir une notion très importante de l'activité spontanée de notre cerveau, qui est évidemment quelque chose dont beaucoup de personnes oublient qu'elle existe. En fait, nous n'avons pas un cerveau qui ne fait que répondre au monde extérieur, mais qui est en interaction avec le monde extérieur. Et cet espace conscient donc a des propriétés qualitatives diverses, et entre autres celle d'un espace où les actions sont remplacées par des simulations. Je pense que c'est une notion importante, où des plans, des programmes et la mise en route des actions sur le monde sont évalués en permanence d'une manière globale, en référence avec donc le monde extérieur, c'est-à-dire l'interaction sensorielle. Je parlerai surtout de ce point-là, c'est-à-dire l'accès des stimuli sensoriels à l'espace conscient, mais bien entendu aussi le soi, les mémoires personnelles, autobiographiques, bien entendu, mais aussi les règles et conventions sociales internalisées à la suite d'interactions épigénétiques au cours du développement de l'enfant, et qui possède donc cet espace conscient, une temporalité et aussi une réverbération du soi sur sa propre expérience, c'est-à-dire une auto-évaluation qui conduit à des prises de décision sur le monde. J'ai pas employé le terme liberté ou etc. Pour moi, ce sont des mots trop philosophiques pour nous intéresser. Essayons au contraire d'analyser ces notions d'une manière aussi pragmatique et concrète que possible, en faisant deux distinctions de base qui pour nous sont très importantes. Les états de conscience, et je ne traiterai pas de cet aspect des choses, bien que un travail récent qu'on a fait avec Stanislas aborde ces questions-là, et je sais qu'il y a pas mal de groupes qui s'y intéressent sur le plan justement de la modélisation. État de veille, de sommeil, d'anesthésie, de coma, de crise épileptique, d'orgasme, ce qui est un problème très important pour les êtres humains, et donc état de conscience, mais aussi évidemment contenu de conscience. Et cet aspect-là des choses qui va m'intéresser, et en particulier un aspect qui est extrêmement important, qui est de pouvoir rapporter d'une expérience subjective. C'est-à-dire que pour nous, le subjectif a une réalité physique, et une de ces expressions de cette réalité physique, c'est qu'on peut faire un rapport verbal, mais aussi par des signes autres divers, de cette expérience subjective. Et je pense qu'il est évidemment essentiel d'arriver à accéder à une description, je vais y revenir dans une seconde, de ces états et contenus conscients en termes neuronaux, et sachant que notre cerveau lui-même est la synthèse d'évolutions multiples. J'ai dit que c'était un objet d'une extrême complexité, mais c'est pas simplement un objet complexe, c'est un objet organisé. Et je pense que ça, c'est aussi une notion que la physique doit assimiler. Comment décrire une organisation, et surtout des niveaux d'organisation qui vont du niveau moléculaire, cellulaire, des circuits neurones, des ensembles de circuits, etc. Donc un des traits de la physique du cerveau, qui selon nous est un des aspects les plus importants de tous et qui est le moins envisagé par les modélisateurs, c'est l'architecture. C'est-à-dire arriver à comprendre comment les architectures neuronales se sont développées au cours de l'évolution, comment ces architectures neuronales, qui sont souvent résultat d'expressions géniques, ont pu conduire à des ouvertures vers le monde au cours du développement ontogénétique, en particulier lors de la formation des synapses. Donc il y a des évolutions emboîtées qui passent évidemment après cette évolution épigénétique essentiellement pré- et postnatale à la dynamique de la pensée et les évolutions culturelles et sociales. Donc on ne peut pas traiter de tout à la fois, mais il faut savoir que quand on fait un modèle en physique, de physicien pour traiter du cerveau, savoir où on se situe. Or on se situe dans une marge qui est extrêmement modeste de cet ensemble de la complexité neuronale, et que je pense que les grandes théories sur le cerveau devront prendre en compte ces principes d'organisation, sinon je pense qu'on perd son temps. Alors on essaye de modéliser des fonctions beaucoup trop complexes à partir d'éléments de base qui sont beaucoup trop simplistes. Le cerveau n'est pas un tas de molécules qui interagissent de manière coopérative, c'est pas un verre de spin, chacun le sait, et il y a toute une organisation qui aussi, et ça c'est un point très important, qui contient une énorme contingence, ce qui est aussi difficile à comprendre pour la modélisation. C'est-à-dire qu'on n'a pas affaire à un système qui est modélisé de manière rationnelle. C'est-à-dire le cerveau n'est pas un objet qui peut produire de la raison, mais qui lui-même n'est pas organisé de manière rationnelle et minimale. Et il faut bien se rendre compte de ça, parce qu'il y a donc toutes ces évolutions successives qui ont donné lieu à des interactions contingentes avec des environnements variés et à partir de données génétiques elles-mêmes très diverses, et que de ce fait, on a des structures, je dirais, qui sont non rationnelles. Je vais pas employer le terme irrationnel dans l'organisation du cerveau, mais dont on ne peut pas comprendre en physicien qu'elles soient ni minimales ni optimales. Et je crois que c'est ça la grosse différence. Ce qui ne nous empêche pas, évidemment, de faire des modèles, entre autres en ce qui concerne la conscience, de prendre en considération que le mot conscience est un mot qui a un contenu sens extrêmement riche et parfois inutile de ce fait. Je me rappelle une discussion que j'avais eue avec l'ancien directeur de l'école normale supérieure qui je disais que les discussions entre philosophes et scientifiques sont toujours très difficiles parce que on ne sait jamais de quoi on parle. Mais il avait répondu, mais si vous enlevez la richesse du sens d'un mot, à ce moment-là, vous perdez tout son contenu philosophique. Donc, avec le mot conscience, c'est un mot adéquat parce que ça veut dire 1000 choses différentes. Et justement, nous avons à créer de l'ordre dans le système et essayer de définir des niveaux à la fois d'organisation et de fonction. Et j'en mets quelques-uns ici. Je ne vais pas passer beaucoup de temps à les décrire, mais simplement pour vous dire que, évidemment, un nouveau-né n'a pas des niveaux de conscience, ne serait-ce que sur les contenus de conscience, parce que vous avez des états de conscience. Il s'éveille, il dort, il rêve, mais sur le plan du contenu de conscience d'un nouveau-né, évidemment très différent de celui d'un enfant de 8 à 15 mois qui commence déjà à avoir des attentions partagées, des interactions sociales très importantes, et bien entendu des enfants de plus de 2 ans qui ont déjà la capacité d'imitation et de reconnaissance de soi par la thèse du miroir, comme les chimpanzés, et puis vers 3 à 5 ans, la théorie of mind, la capacité d'attribution, c'est la capacité de comprendre les états mentaux d'autrui. Donc juste pour illustrer le fait que il faut examiner les questions de conscience chez l'homme en particulier, en étant averti de ces niveaux d'organisation et qu'on ne veut pas essayer de décrire tout à la fois. Donc en ce qui nous concerne, nous sommes déjà au niveau de la conscience minimale, au niveau de la modélisation, et nous n'avons pas la prétention d'aller beaucoup plus loin, sauf évidemment dans les années à venir, il faut espérer, où on pourra accéder à des niveaux d'organisation beaucoup plus élevés. Et je pense que la modélisation en termes neurobiologiques est très loin du compte actuellement. Alors juste un mot pour les modèles. Alors je crois que à cet égard, les biologistes ou neurobiologistes qui s'intéressent au cerveau sont aussi et doivent être des physiciens. S'ils ne le sont pas, ils doivent collaborer avec des physiciens ou des personnalités qui sont suffisamment expertes pour les aider dans leur modèle, ce qui est mon cas, et on essaye donc de saisir une fonction. Alors là, par exemple, ce que j'ai appelé la conscience minimale, c'est-à-dire ce qu'on pourrait appeler les fondamentaux de la conscience, et justement d'essayer là de les décrire tels qu'ils sont avec un modèle minimal, c'est-à-dire d'essayer de retrouver les architectures neuronales telles qu'elles existent et non pas telles que nous pouvons nous les imaginer, et d'essayer à partir de ce qui existe de le décrire de manière minimale. Alors je tiens à souligner que là c'est un aspect intéressant, c'est-à-dire que la physique nous aide dans la description, mais pas tellement dans la compréhension. La compréhension, nous devons être en quelque sorte soumis à l'objet physique que nous avons devant nous, qui est encore une fois le produit de ces multiples évolutions, et essayer de comprendre comment il est organisé. C'est-à-dire que c'est là où je crois qu'il y a une très grande différence dans le raisonnement du physicien standard et du neurobiologiste standard, en ce sens qu'on essaye de faire un modèle théorique sur un objet, encore une fois, d'une extrême complexité, dont nous essayons de saisir les éléments critiques et de les décrire sous une forme minimale. Et je crois que c'est un point très important. Et dans le but d'établir une relation de cause à effet entre un processus qui peut être, dans le cas justement de l'espace conscient, un processus subjectif et une description objective de données neuronales. C'est-à-dire que, à titre d'exemple, vous êtes en train de m'écouter, vous me regardez avec des yeux pleins d'intérêt, enfin j'espère, et vous avez dans votre tête, évidemment, une perception subjective de ce que je vous raconte, avec en même temps, dans votre espace conscient, dit non, il nous raconte des histoires, tout ça c'est pas vrai, moi je suis un physicien qui fait ceci, ou je suis un biologiste qui fait cela. Donc tout ça c'est du subjectif. Eh bien, ce que nous essayons de faire, mais d'une manière évidemment beaucoup plus simpliste, sur des tests cognitifs, une relation entre un processus subjectif et des données objectives qui sont les données de la physiologie ou de l'imagerie, ou que sais-je encore. Donc, notre but, c'est d'établir une relation causale. Je pense que cette notion de causalité est extrêmement importante. On n'en est pas au corrélat de la conscience, mais à la mise en place d'une relation de causalité, de cause à effet entre l'objet physique qui est le cerveau et ce qui est produit par cet objet physique, c'est-à-dire de la subjectivité. Donc c'est encore une fois un projet qui doit conduire à une expérimentation. Et nous nous sommes avertis, contrairement à certains physiciens qui croient que la mécanique quantique donne une description complète du réel, ou se substitue même au réel. Certains collègues physiciens m'ont absolument étonné en pensant que leur théorie était ultime, c'est-à-dire qu'elle décrit le réel, et puis le reste, on s'en fiche, on n'a plus rien à faire, on est là en face d'une pénétration du réel par des objets mentaux créés par le physicien. Alors ils oublient, ça c'est ma traduction, ils oublient que ce sont des objets mentaux. Et donc ce sont toujours des produits de notre cerveau, et qu'il n'y a aucune raison que les produits de notre cerveau, que ce soit sous la forme d'une belle équation mathématique, puissent donner une description exhaustive du réel. Et là je crois qu'il est extrêmement important d'avoir ça en tête, et nous, neurobiologistes toujours très humbles, nous savons que les modèles que nous produisons sont toujours incomplets, imparfaits, et nous n'avons pas la prétention qu'ils donnent une description exhaustive de la réalité. Et je pense que cette notion, John Searle, d'ailleurs, le philosophe, l'a envisagée, je pense que c'est une notion extrêmement importante, et qui pour nous est évidente, je ne sais pas spécialement par humilité, mais par bon sens, alors que des physiciens extrêmement avertis, très performants, peuvent totalement oublier cet aspect-là des choses. Et j'ai eu des contacts avec des physiciens qui me le montraient. C'est pas de la médisance, c'est un fait. Donc, j'ai essayé très brièvement, il me reste combien là
5 minutes.
5 minutes. Bon, de vous faire voir comment j'ai passé on peut essayer de modéliser cet espace conscient avec l'idée qu'on va se concentrer sur un aspect donc de l'espace conscient, c'est la capacité d'intégration globale et de représentation unifiée du monde. C'est un aspect que j'ai donné dans la définition de tout à l'heure, où on a à la fois la perception, la mémoire et la planification. Tout ça dans un monde qui paraît être unique. Cette fameuse unicité, au moins à certains stades de traitement de l'information, il y a un moment où ces choses sont unifiées. Alors l'idée, qui est très simple, c'est qu'on a eu avec Stanislas, c'est de se référer à ces vieux travaux de Ramon y Caral, sur lesquels il existe dans le cerveau des neurones à axones longs, et qui vont de la partie antérieure, postérieure réciproquement du cerveau, c'est qu'ils réunissent entre eux des aires très diverses, et même ils sont susceptibles de réunir les deux hémisphères ensemble. D'où l'idée qu'on puisse avoir une globalisation par des ensembles de neurones extraordinairement diversifié et réunissant des territoires très, très divers de notre cerveau, sachant que ces neurones axones longs se trouvent localisés dans les couches 2 et 3 du cortex cérébral, et que quand on regarde ce type de cortex numéro 2, on voit qu'il se situe essentiellement dans le cortex frontal et aussi dans le cortex pariéto-temporal, et que, en fait, au cours de l'évolution, ce sont des territoires qui se sont développés d'une manière fulgurante au cours de l'évolution humaine. Donc, vous voyez tout de suite que si ce cortex-là se développe au cours de l'évolution, eh bien, la capacité de l'espace conscient lié à ces neurones à axones longs est susceptible de s'accroître aussi de manière extrêmement simple du fait d'un accroissement de surface différentielle de certains territoires corticaux. C'est intéressant, c'est que Patricia Goldman-Raki, bien longtemps, avait déjà proposé l'existence de ce type de circuit entre frontal, pariétal temporal et cortex singulaire, et lui-même lié évidemment au système limbique qui est en relation avec, comme vous le savez, les émotions. Donc voilà, juste pour illustrer cet accroissement de surface du cortex frontal et également l'accroissement de l'interconnectivité corticale au cours de l'évolution. Et l'idée générale, c'est que nous avons proposé, c'est qu'il puisse exister deux espaces computationnels, en simplifiant les choses, des systèmes de processeurs spécialisés et automatiques, comme les systèmes perceptuels, de la vision, de l'audition, système moteur, de l'attention, la mémoire à long terme, évidemment, et toute la sémantique, et aussi des systèmes d'évaluation, et que reliant tout cela, ces systèmes de neurones axones longs qui forment un espace de travail global, qui relie entre eux ces divers territoires et crée une expérience subjective consciente. Et à ce moment-là, l'accès à l'espace conscient peut se passer des processeurs à l'espace de travail. Et dans une modélisation récente, nous avons montré la non-linéarité de cet accès dû à des systèmes de circuits rétroactifs dans le traitement de l'information des aires corticales primaires au secondaire jusqu'au cortex frontal. Et l'idée étant que on puisse avoir des modes de traitement évidemment très différents au niveau des processeurs, au niveau de l'espace conscient, avec ce que nous avons appelé une ignition dans l'espace conscient qui est due à la mobilisation d'ensemble de neurones à axones longs qui eux-mêmes seraient en contact avec des territoires divers du système des processeurs spécialisés. Donc c'est un modèle d'une extrême simplicité qui a l'avantage de pouvoir être modélisé et d'être donné un certain nombre de prédictions et entre autres de prévoir des réponses différées, enfin des tests comme par exemple le test de Stroop, la tâche de Stroop qui est une tâche cognitive bien connue, mais aussi d'autres systèmes, et je vais juste vous montrer 2-3 expériences qui vont dans le sens de nos idées. J'ai bientôt fini. D'une part, l'imagerie de l'anesthésie générale et du coma qui montre que ce circuit que vous avez pu voir tout à l'heure, qui frontaux, pariéto-temporaux singulaires, en fait se trouve considérablement réduit dans ces travaux d'imagerie sur les états de coma, d'anesthésie générale ou l'état végétatif, donc que l'état conscient est effectivement lié à des territoires qui sont proches de ceux que nous avons prévus. Vous montrez une expérience simple de traitement conscient et non conscient. Chez le sujet vigile, on fait succéder ces diapositives. Vous voyez que le mot lion ici était situé entre deux blancs, alors que là, le mot note est situé entre deux masques. Vous voyez l'échelle des temps. Et si maintenant vous demandez au sujet ce qu'il a vu, il dira ici j'ai vu lion, ici j'ai rien vu. Donc il y a un traitement conscient et un traitement non conscient. On sait que le mot note ensuite peut être utilisé dans d'autres expériences qui font intervenir du priming, par exemple, l'amorçage non conscient. Donc il y a eu un véritable traitement par le cerveau. Et voilà les images que vous obtenez. C'est Stanislas Dehaene qui a fait tous ces travaux dans son groupe au CEA, à Saclay. Et vous voyez un traitement cortical conscient qui justement va mobiliser le cortex préfrontal et donc l'espace de travail comme nous l'avons postulé. Et là, au contraire, dans le traitement non conscient, seulement des aires qui sont mobilisées pour le traitement de la forme des mots. Et vous voyez très très peu de mobilisation des territoires mentionnés et des territoires qui sont avec ces neurones à axones longs. Ceux qui trouvent que je vais un peu vite peuvent lire L'homme de vérité. Tout ça est exprimé déjà décrit de manière très explicite. Juste pour dire que ces états physiques peuvent être suivis par les méthodes de l'imagerie que nos physiciens nous ont très gentiment apportées, comme la résonance magnétique et aussi l'électroencéphalographie. Vous voyez que vous avez des images très différentes quand il y a un traitement conscient d'un mot visible et un traitement avec masquage. Donc on peut suivre au fil du temps l'accès à l'espace conscient et vous voyez bien entendu très clairement ici dans le traitement conscient l'extraordinaire contribution du cortex préfrontal après 244 millisecondes. Donc ces travaux peuvent être étudiés par ces méthodes physiques, mais aussi bien entendu pour le modélisateur par en utilisant les modèles que j'ai mentionnés. Qui ont été publiés. Si ceux qui s'intéressent peuvent aller voir cet article qui est au Proceeding of the National Academy of Science. Et vous voyez qu'ici, nous avons une simulation dans un système artificiel, bien entendu, et très simplifié, où il y a le traitement conscient, et ici, le traitement non conscient, et pas de mobilisation d'activité pour le traitement non conscient. Donc, je terminerai là-dessus et pour vous dire que on peut aussi s'amuser, mais ça sera pour un autre exposé, à faire des expériences chez la souris. Alors, évidemment, question posée, est-ce que la souris est consciente ? Alors, ça fait rire tout le monde. Je pense qu'elle a quand même des traits minimaux de cette conscience de base. Hein, et c'est vrai qu'elle s'éveille, elle dort, elle a des planifications d'action relativement modestes. Et les travaux que nous avons en cours à l'Institut Pasteur sont justement sur des animaux transgéniques modifiés au niveau génétique. Et ce que nous essayons de montrer, c'est que quand il y a, par exemple, la perte de certains types de récepteurs qui sont sensibles à un neurotransmetteur endogène, eh bien, ces aspects qui peuvent être reliés d'une manière discutable avec l'espace conscient sont altérés et qu'on peut par exemple les récupérer par réinjection de virus, de l'antivirus qui contiennent le gène et les récupérer dans des territoires très particuliers du cerveau comme ceux qui sont engagés dans les systèmes de récompense. Donc je pense que la souris va devenir un petit peu la drosophile de la conscience, je me permets de faire cette métaphore, car je pense que nous disposons maintenant d'une quantité d'éléments génétiques utilisables avec ces animaux. Alors, est-ce que la souris est vraiment un organisme qui a une conscience ? Je dis oui, si on considère qu'il y a plusieurs niveaux de conscience.
On va passer directement à Vincent, qui va nous parler des relations entre la physique statistique et la neurophysiologie.
Should I speak in English or? Okay, very good. Why? You don't understand French. Okay, very good. So, sorry for my broken English. So so I'm not used to speak in front of such multidisciplinary audience, as Jean-Pierre was saying. Okay, so I will speak about statistical physics and neurophysiology. And so maybe it will be an opportunity to, first of all, dissipate some misunderstanding, maybe, and also to see that different communities attribute different meaning to the word modeling. And also I will disappoint you because it will be much more specific than maybe you think physicists are doing. So first of all, there is one aspect that is very clear, is that physics brings nice experimental tools. As Jean-Pierre was saying, there is RMN, single molecule manipulation. You have heard yesterday about them, different kind of microscopes, X-rays, etc. So this is clearly useful since detailed experiments, we believe, are necessary to understand biology. So the point that is perhaps less clear is what theoretical physics can bring to biology. And so to illustrate that and to give you a feeling for that, that is not based on some preconception but on what really people do, I will take two examples of our recent research. Okay. So I've taken two examples. One is something that is trying to understand the synaptic strength at a particular synapse in the cerebellum. So this is the parallel fiber Purkinje cell synapse. This is work in collaboration with our colleagues in the neurobiology department. And the other is about neural rhythm and how do they emerge, what are their characteristics. Okay, so first of all, why are people interested in synapse? Is because at least in part memory are thought to be stored in synapse and in their modification. So this is one particular aspect, and if one wants to study this quantitatively, one has to study a particular kind of a well-defined synapse in some sense. So this is what Philippe Izop and Boris Barbour, that are working in the neurobiology lab, did. I will show you the detailed anatomy afterwards. But what they did is that they measured the strength of this particular synapse. They measure several hundred of them, and so when you have several hundred numbers, you can draw an histogram. So they draw this histogram. So this is already interesting. You can wonder how this you can understand the value that you find. But they also found something that was very striking in some sense, is that most of these synapses were silent, meaning that there is no current that passed through them, no information in some sense. So, and it was more than 80% of these synapses were silent. So this is a qualitative question. Why, in this particular experiment, you find so many silent synapses? So actually, we met them in a Chinese restaurant, and they asked us this question. And so we started to think about it, and I will show you how maybe a theoretical analysis can bring new ideas. I mean, on this question, maybe these ideas are not right, but at least they are new. So, okay, so first of all, I remind you what is the architecture of the cerebellum. So the cerebellum, the cerebellum is thought to be useful to acquire precise sequence of movement, like when you learn to play tennis or things like that, complicated thing. So there is information that is brought about the sensory information and information about the position of the body is brought here to this granule cell, and then these granule cells are transmitted, have axons, that make contact to this Purkinje cell, and then the only output of the cerebellum is this axon of the Purkinje cell. So there is input and output. And of course, there are many cells in between also. And there is a particular cell that is this, here there is this climbing fiber. And this whole architecture actually, people see it, and the idea about it is coming from, not the architecture, but what it does is coming from a very influential theoretical proposal by David Marr in 1969. And the idea is that you modify here the synapse under the control of this professor, this climbing fiber. So if the output is not what you want to do, if you miss the ball, then this in some sense fires and you modify the synapse. Of course, it's very simplified. And there are some experiments, in particular by the group of Ito in Japan, which provide some evidence for that. Okay, so this is already some theory about the cerebellum. Okay, so this is the principal actor. And I show you this, first of all, because it's a very nice picture by Boris Barbour, also so that you have an idea of what a Purkinje cell is, and also to contrast it with the spherical cow of the physicist that comes on the next slide. So this is our Purkinje cell. So it's a very simple model. We say that we keep this parallel fiber, this synapse, and this cell, and this is the output. Okay? So what the cell has, and we would take the model from this proposal by David Marr. So what we say is that the cell has to classify things. So I have taken a visual analogy to make that quite clear. So you have information coming from this parallel fiber. So I take a visual analogy, and you can think that each of these fiber is bringing information about a picture. So either the pixel is white or black, and what you have to decide is this picture is if this is a picture of a physicist or a biologist. So if it's a physicist, you spike, and if it's a biologist, you don't spike. Okay? So this is the task. Okay, so you have a batch of picture. You don't know anything about them, but then I'll teach you what it is. So this is physicist, biologist. Okay, so by the way, this is Elisabeth Gardner, and all of our theory is based on method that she developed. So you understand that this is a basic task, okay? So here some number, this number of parallel fiber that make synapse with this Purkinje cell is about 150,000. And so how this thing works. So now this is the architecture, but now we are going to simplify it a lot, saying that this Purkinje cell is just doing linear summation with threshold. So if there is a white pixel here, you depolarize a little bit the Purkinje cell, and how much you depolarize it depends on the weight that you put here, and then you sum it, and if it's above a threshold, you emit a spike. So this is a very simple model, okay? Okay, and so if you want to learn robustly, you have to learn to be above a threshold plus a security margin, and otherwise you don't spike if you are below the threshold with a security margin. So this is how the physicists see the model. So now the model is precise, so you can analyze it precisely. And you understand that, okay, you can, with a single cell, this single, even simplified cell, you can learn a definite amount of image. You cannot classify as many images as you want. So this is a number that can be computed, thanks to Elisabeth Gardner. And then what we decide to do is to suppose that the Purkinje cell learns as much as it can, and then compute in this simple model what is the distribution of weight. So each time you learn, to discriminate things, you have to adjust this weight, and then if you learn as much as you can, there is a very well-defined distribution of weight here. So you can compute it, and compute it means making some simplifying assumption again. So one assumption is saying that there is no correlation between, here in this visual analogy, the picture and the activity, meaning that, okay, there is basically Elizabeth Gardner could have been a biologist. So given the picture, there is no very real correlation. Not all physicists are dark hair. Not all biologists are blonde, for instance. So this is a simplification. We say that the proportions are the same. Okay? And a second assumption is that here the pixels are black or white with certain probability. There's no correlation, which for picture would certainly be wrong. Okay, but given this assumption, you can compute the distribution. And the striking theoretical result is that when you do that, in this mathematical model, you obtain that in any case, there are a lot of silent synapses in the mathematical, more than 50%, and this can be up to 100%. And the reason is that all these synapses are excitatory. So when you optimize something, when you optimize, you can increase the weight of the synapse or decrease it. But since it's bounded by 0, you cannot go below 0. And the mathematical result is that there are always more than 50% synapse, and the exact number depends on the security margin over the threshold. And then when you have done that, then you can fit, of course, the experimental data, and this is a comparison. Okay, so then you can make some prediction about the numbers, etc. Okay, so what this summarized theoretical analysis has told us. So it has told us that, okay, maybe one reason for that one sees all these synapses that are silent is just that the Purkinje cell is, in fact, learning as much as it can, So this is a hypothesis. A natural question is why these synapses are kept. And the idea would be that if you just remove them, then you cannot learn a new set of association. And then there is a even more interesting idea that the fact that synapses are silent may be much more general than the cerebellum. So you see that this analysis has given us a slight a perspective that is rather different from just looking at the brute data. How many minutes? J'ai combien de temps? 10 minutes. 10 minutes, okay. So the next subject, so in the model, you have seen that this Purkinje cell respond to synchronous input in a millisecond time window. So there are general questions associated to that. Is what are the modes of information coding in the brain? What are the mode of activities? And there are a lot of interesting questions there. So just as an example, I will take the case of neural rhythm on a particular example again. So people are interested in oscillation in the brain for very different reasons, but also because oscillation are seen in very different tasks. Here it's an experiment by the group of De Simon, which I won't explain the detailed experiment, but the idea is that if you pay attention to something, then the power in the oscillation is very much increased. Okay, so that people think that maybe this is related to attention or maybe even to consciousness. Okay. So also when a rat is performing different tasks like moving, you see oscillation in the theta range around 10 hertz. here you have very fast oscillation during sleep. And so there are oscillation in all kinds of different tasks. And one nice feature for us, since we are interested in rather precise thing, is that you can also reproduce this oscillation in slices. If you take, for instance, hippocampal slice and you put some agonist carbachol, you can depolarize a little bit the cell and create oscillation in the dish, so you can study them quite precisely. Okay, so what is the... So, of course, there are all kinds of different problems here. One question that I just will discuss is how these oscillations appear. So here you see this fast oscillation, and here are recording of a neuron in the brain. So here pyramidal neuron and here inhibitory interneurons. So here is a trace. Probably you don't see anything, but here this neuron fires, emit a spike only here, and not here, and this one here, this one here. So they are even the interneuron, they fire more often, but not at all these period of oscillation. So first of all, this looks very different from the usual picture of synchronization. The usual picture is for oscillation is that you have oscillator and that you synchronize them. And this looks very different. Each neuron is not an oscillator. And the question is this even possible? Or are there hidden oscillators that you don't see in this recording? And if this is possible, what are the characteristics of this oscillation? What sets the frequency? Things like that. Okay, so I remind you, this is the standard picture of synchronization. It goes back to the discovery of Christian Huygens. So this is in French. For those who can read in French, it starts rather trivially. So Huygens is ill in his bed, and he looks at his two clocks. The two clocks are the better clocks of his time, and since they are very good, he remarks that actually they move together, and this gives rise to the discovery of synchronization. So the idea that goes back to Huygens is that if you have oscillators that are close in frequency, that you couple them, then you would have a global oscillation. But you see that, and this of course has been applied to many things. It's also true for some reason that what people see in the brain. But for this sleep rhythm is certainly not true. You have seen that all these there are no oscillator to begin with. So to investigate that and to see if it is even possible, we decided to take a very simple network. So here we just connected the simplest kind of neuron, which are just the simplest model is the same kind as what I showed for the Purkinje cell. It's a linear integrator, leaky linear integrator with a threshold, so it receives input and then the spikes. So this is driven by random stimulation from the outside, and then there is all these neurons are coupled, not all coupled together, but coupled randomly. And the idea, and we put a synaptic delay, meaning that if one of these neurons is active, it inhibits one of the other with some delay. Okay, so this is the simplest model, a very big caricature, of course, of the real thing. But the interesting point here is that even in this very simple setting, you can see that you reproduce the phenomena that if the collective oscillation you see, and each neuron is not an oscillator. So now, this is of course very simple, but given that you see the phenomena in a very simple setting, you can analyze it completely in this setting. And for instance, ask the question, what is the frequency of this oscillation to what it is related in this neuron? So you can do do it. There are simple several time scales that you can think of, the membrane time scale, the firing rate. And a simple argument suggests that maybe it's synaptic transmission that is important here. I mean, if there is a little bit more activity in the network at some point, since all these neurons are inhibitory, then there will be less after a time delta, time to transmit the information. And since there is less inhibition at the time t plus delta, there will be more at the time t plus delta. So this would give a guess of the oscillation frequency. This, in fact, works quite well. And then you can also see that there is show that there is a threshold for this oscillation, and in fact analyze this thing with various degrees of precision and complexity. So why is it useful? So first of all, it is useful because you know that this is possible. This is a phenomenon that is possible. If you take things that do not oscillate, that you couple them, you can have a rhythm that is emerging. And this also provides a basis for developing more complex model. Once you have understood that, you can construct assemblies with different kinds of neurons, excitatory, inhibitory, more detailed description of the synaptic current, and go closer to the experimental situation. And then you can take into account specific properties of this neuron, like resonance at particular frequency. And in fact, this is an ongoing process because there is a lot of recent experimental data on the dynamics of various classes of interneurons in this rhythm, and that you can try to understand. So just one example of this, of this more complex neuron is that here you see that different neurons are resonating. This is an experiment in the group of Paulsen at Oxford. And they have resonance at different frequencies that are peaked at frequencies that you see in the collective rhythm. So this asks the question why this neuron have this resonance. So instead of answering this question, I'll just conclude. So this work I've reported the distribution of synaptic strength was done with Nicolas Brunel, Jean-Pierre, who will speak afterwards, Boris Barbour and Philippe Izop. And so you see that Nicolas is working in a lab, it's called neurophysics, which is already some strange mixture. And the work on neural oscillation was performed with Nicolas and Magnus Richardson in it's even more grandiose name, is Brain in Mind Institute. Okay.
So we will have now Ravada Silvera, who is going to talk about nouvelle cuisine in the brain.
Well, it's a great pleasure to talk here, especially after Jean-Pierre and Vincent, who are both experts in the field. By contrast, I'm a relative newcomer to the field, and so I'll keep the discussion at a much more concrete level. I've also decided on a less ambitious title. And now, in the very last transparency, I'll tell you why Nefertiti and why Bocuse. But in the meantime, I'm not going to talk about either Egyptian royalty or French cooks, French royalty. But the main actor in the talk will be the retina. As you all know, the retina is a tissue, is a very thin sheet of tissue that is lining the back of your eye, and that is responsible for vision. And it's not only regular tissue, it's neural tissue. It's the tissue that the brain is made of. And because it's the cells that it's made of are cells that also occur in the brain. And not only that, but the retina actually grows in the embryo as a little piece of the brain advances towards the eye. Now, the specificity of the retina is that it reacts to light. So when light comes from the external world, it gets imprinted on the back of the eye in the retina, and then the retina sends a message to an intermediary relay station in the brain, in the middle of the brain, and that is sent to the back of the brain, here in the back of the head, where sit your visual areas. Okay? And from those visual areas, there are messages sent to all over the cortex, and roughly speaking, in human beings, about 40 to 50% of your head, of your cortex, is busy dealing with vision. Yeah? Okay. All right. Okay. So whatever is lost by the retina will be lost forever in your brain. And whatever is emphasized by the retina is emphasized forever in your brain. So what my aim in this talk will be twofold. First, I want to show you that the retina actually does many things that you would have thought the brain is doing. What I mean by this is that the retina is processing very heavily what the visual world before it sends a message to the brain, and that processing is a very active processing in the sense that the retina is constantly adapting to the world. My second aim will be to just illustrate some of the mechanisms that the retina uses to do that processing and to try to convince you that you need some mathematical language, some finer ways of understanding those processes. So the image that you may have of the retina and the image that people have until, say, roughly the war is that it acts like a photocopier, like a Xerox machine. That you take a point of light, gets imprinted on the retina, another point gets imprinted somewhere else, makes a photocopy of the world and sends that photocopy to the brain. Now, this is a very poor representation of what the retina does. A much better representation is that of a factory which takes in some signals, here a tree, a palm tree, and the little men in the factory who look like me treat those signals and kick out some representation of these signals, here just the word tree. Okay? Now, in the case of the retina, the signals that are sometimes called inputs or stimuli are just patterns of light. Here, bars of light. The light is sent on the retina, and cells in the retina reacts to those lights, to that light, by generating some electrical activity that is sent to the brain. And you can record that electrical activity with an electrode, and you find some variable electrical activity, which is the actual representation that the brain gets of that signal. Okay? So now you could ask a million questions about this, but you could summarize all those questions by saying, what is the code of that representation? In other words, what is the vocabulary that the retina is using in writing up its message? Okay? Now, if you want, you'll of course choose your vocabulary depending on what you want to describe. I'll choose a cooking vocabulary if I want to describe a dish. So the first thing we have to look at is what is the range of the inputs that are coming into the eye. Now, what is very surprising is that this range is enormous. Okay? So, for example, at starlight, in the middle of the night, if you're walking in the streets, you can still see things. You can walk around in the streets unhindered. And you'll get very, very little light in your eyes. You'll get about 1 photon per minute per cell in the retina. That's very little. Okay? Now, in broad daylight, so about noon, you'll get about 100 million photons per minute per cell in your retina. That is, if every photon were a peanut, you would be getting about 100 bathtubs full of peanuts in each cell in your retina during each minute. Now, I don't know any other machine that can work under such a range of inputs. Okay? So how does the retina cope with that? Well, one way it copes with it is that it doesn't send to the brain actually a message about the intensity of light, but it sends to the brain a message about comparison between different intensities in neighboring points. So, for example, if you look at the room of Van Gogh in Arles, you might have a lot of light coming in your eyes. So the average amount of light might be very large, like so. Okay? However, if you compare nearby points, like here and here, it's nearly the same amount of light that arrives in your eye. So if I look at how the amount of light moves from point to point, it spans a much smaller range. Okay? And what is sent to the brain is actually those differences and not the whole thing. Now, to understand how this is done, we have to go and look in the guts of the retina slightly more in detail. So I've blown up for you, this is the retina in the back of the eye, this is a blown up, and I've drawn here a simplified diagram of the retina. So the way it works is that at the top of the retina you have photoreceptor cells here that react to light when light arrives, it will excite a photoreceptor cell. That excitation will be sent to that red cell, which is called the bipolar cell. And the bipolar cell, in turn, will excite the purple cell, the ganglion cell, which will send a message to the brain. Okay? So that's an excitation pathway all the way to the brain. Now there's also an inhibition pathway, because if light arrives here, it will arrive in this round cell, which is called an amacrine cell. The names are really unimportant, but it's called an amacrine cell, and that amacrine cell, instead of exciting this ganglion cell, will inhibit it, will suppress it, okay? So if I look now at the top view of the retina, and if I send a spot of light smack right on top of the ganglion cell here, I'll get a positive response. But if I'm also sending some light laterally here, that response will become weaker because of the suppression coming from here, okay? So this is a very important notion, and I'll use it again and again, so remember it. I'll explain it a bit further in the next transparency. But these kinds of structures that describe how a given cell in the brain responds to light are called receptive fields. And here, this one would be called a center surround receptive field, because it has a positive center and a negative surround. Okay? So this experiment is not just a theorist's dream. You can, of course, do this experiment, and you do it pretty much in the way I've described. So you take a screen, you show some movie, some pattern of light that is sent on the retina, maybe on the cell, maybe nearby, and then you measure the response. Now, those experiments are done in kind of a horror film fashion, because you take a rabbit or a salamander or something like this, and you pluck out the retina, and you put the retina on a dish, which looks like this. And the retina is lying flat on the dish, and it survives for about 8 or 12 hours. And from that, you show a film, and then you record from under the retina what is coming out, so that's what's going to the brain in the full animal. So here's a blown up of the retina, and what you see are these black things are electrodes that are picking up electrical signals from cells, and the green things are the actual cells of your retina, which are talking to the electrodes. Okay? And just as a side remark, it's because of such tools that one is able to get very precise data and start thinking theoretically. So what happens? So what happens is if you shine light smack right on the ganglion cell, you'll get a moderately positive response. If you send light on the surround, you get a negative. You get a response, but it's negative. It's a repression. If you send light everywhere, you get a near cancellation, which means that if you're calculating differences, so it's everywhere the same, your brain basically doesn't respond, or just very little. And if you put light in the center and shadow around it, then you get a very strong response. Okay? So the retina is all the time calculating differences and sending that to the brain. Now, again, you might think that I'm a bit crazy, so I want to show you this. So if you're normal human beings, you see this one much darker than this one. Okay? And actually, they're exactly the same color. The reason you see it darker is because you're not seeing what is there. You're seeing a comparison between this and what is around it. And because the surround here is lighter, these things are lighter, and here it's darker, by comparison you see this as being dark. So let me take out the surround for you, and you'll see what happens. So they're the same color. Now, your retinas are not very smart, so you won't remember. So this is what Eugène Delacroix was thinking when he said, give me a dirty mud, and I'll make it into the tenderest flesh. Because what you see is what it is only because it's sitting to something else that looks like what it is, which is also looking like something because of the thing which it was sitting next to in the first place. Now, all that I've described until now are static things. But in fact, as I said, things are changing all the time. And as I said, between midnight to noon, things vary. The amount of light that your eye receives vary by a huge amount. Varies a lot. So, for example, when Van Gogh was waking up in Arles, his room looked a bit like this because he had his shutters closed. Now, he could still see the bed, the table, and everything, and that's because he had pretty good receptive field with a big plus region, okay? Then he wakes up, and he opens the shutters, and suddenly he's blinded, as we all have had the experience. But you're blinded only for a few seconds. And after a few seconds, you can see your room pretty well again. And that's because your plus size has decreased within a few seconds to the expense of your minus region in the receptive fields. Okay? So to summarize this, and some members in the audience know I've chosen this picture. So to summarize this, the view is that in the retina you have these circular receptive fields, but they can change in time as a function of how much light is coming in them. Okay. Now, a major discovery in the 50s and 60s was that if you record from cells in the brain, you also get similar receptive fields with a plus region and a minus region, only they're elongated. They're not circular. So as you see, this is the beginning of the recognition of shapes, okay? Because if you have an elongated receptive field, it's much better at picking up bars of light, horizontal bars of light, or vertical bars of light, while these other receptive fields were pretty good at picking up spots of light. Okay. And the idea is that as you go deeper and deeper in the cortex, you go further up in the cortex, actually here, then you get more and more specialized. So you find cells that respond to crosses and cells that respond to curve, until you get to some cells that respond to the face of your father and other cells that respond to the face of your mother. Okay? So until last year, the picture that people had was that light intensities is the realm of the retina, of the eye, and shapes is the realm of the brain. Now, a marvelous discovery that was carried out in the lab of Marcus Meister at Harvard this year shows that it's not the case. And in fact, already in the retina, you have recognition of shapes. So already in your eye, you're picking up on shapes. Only you're doing it in a dynamical way. The retina is constantly rearranging these receptive fields into shapes to be good at picking up more complicated objects than spots of light. Okay? So here's an experiment that you could do to show that. Okay? So you look at vertical bars for an amount of time, and then you suddenly switch what you're showing your retina to horizontal bars for an amount of time. Okay? And this is roughly what happens if you're walking, as you often do, through a bamboo forest, where the dominant features are vertical features, the trees, okay? And then you arrive to the end of the forest and space opens up and you're in front of a horizon, and the dominant geometrical feature there is a horizontal one. Okay? So what happens if you record the response from the retina, what you see is that it's slowly decreasing, slowly decaying. But suddenly, when you switch from one to the other, you have a sharp rise in the response, and then it starts decaying again. So here, the retina is telling your brain something new has happened. And this happens precisely because the receptive fields are changing their shape. So here you have a circular receptive fields, but it gets bored, so progressively it arranges itself so as to become less sensitive to vertical bars. Well, how can you get less sensitive to vertical bars is that you become more flat. Okay. But by the same token, by the time you're more flat, you're very sensitive to horizontal bars, and that explains why you have a sharp rise here. And then again, you start decaying, and you go, and you change again the shape of your receptive field. So what you see is what the retina is calculating on the world and then sending to the brain. Okay? So in a very literal sense, the English saying, according to which the beauty is in the eye of the beholder, is true. So now the important thing is that here, this thing is very fast. It takes a few seconds or a few tenths of a second for this change to happen. So now if we want to try to understand how it happens, we have to go and look in the guts of the retina again. So just to remind you what we said before, when light comes in, there's an excitatory pathway that goes from photoreceptor to ganglion cells to the brain. There's a direct inhibition through amacrine cells here. And what I had hidden from you until now is that there's also an indirect pathway because amacrine cells also inhibit precursors to ganglion cells, bipolar cells. Okay? So if I look now at the top view here of the retina, I've illustrated the direct inhibition on the right and the indirect inhibition on the left. And then the question is the following, is if I light this with a bar of light like this, how will this ganglion cell change its receptive field? Okay. So clearly it must be either because of a modulation of inhibition or because of a complicated modulation of excitation. And you can construct two different mechanisms that are based on these two principles. Okay. So let me go over these in a qualitative way. So the first mechanism is based only on inhibition. Okay, so that's why I've forgotten about the excitatory, the red cells. I'm putting only the blue cells that are suppressing the activity. So if I put now a bar of light here, what will happen is that these round cells will be active at the same time as the ganglion cells, as the circular cells. And the prescription says that if you have two cells that are coactive, their connection strength will increase. So these points, these connections will become stronger. As a result, you see, I will have more vertical inhibition than horizontal inhibition, and my receptive field will flatten out. Okay. Now, why have I called this a learning mechanism? It's because, as Vincent mentioned, it's believed that the brain uses a very similar principle of strengthening connections of coactive cells for storing memory. So memory in the brain is believed to work in a very similar way. And you can see why it would be a good way, because in memory is precisely what makes association, and here you're making an association at at the cellular level. Okay? So I think it's extremely interesting that maybe the same mechanism that is in play in memory could be in play in vision. Okay? Now there's one problem, is that this is typically much slower than a few seconds in the brain. It takes minutes or even more. So here's another mechanism that one could think about that is faster. Okay. Now I'm not going to go into the details of this mechanism. Let me just mention that it's based on a very different principle. It's based on a principle not on the strengthening of coactive cells, but just on the fatigue of a given cell. And this principle here says that if a cell like this one is active for some amount of time, a few seconds, then its connections will become weaker. Okay. And as you can see, these will also have the result of flattening the receptive field. Well, not quite. That's not quite enough. I also need some cooperative actions from modulation from inhibition. And that's why I'm saying that this mechanism is not only based on connections like this one, but it's based on connections plus some more broader notions of network architecture in the retina. But in any case, the basic idea is that this is not the same mechanism of memory, but it's a mechanism that ensures for you stability. If you're very active for a long time, you become tired, so that prevents you from being too active. And that's precisely what the mechanism that is there to prevent, for example, epileptic seizures, to prevent the activity of the brain to go crazy. Okay. So, if you haven't followed the details of these models, it's not very important, but the bottom line is that you have two models that are based on two very different conceptually very different mechanisms, but they both give rise to the proper answer in words. Okay. So one needs a finer way of distinguishing the two models. Words are just not enough in this case. And the finer language is precisely the language of mathematics. So I don't want to go through this in details. I just want to flash this for you, for those of you who are more technically inclined, and I'll just go through this rapidly, and then I'll just have a couple more transparencies. So, okay, so in the learning model, the activity of a ganglion cell is a function of the activity of its precursor, the bipolar cell. Similarly, in the fatigue model, the activity of a ganglion cell, whatever is sent to the brain is Y, and it's a function of the activity in the bipolar cell. Okay. Only in the learning model, the positive gain, which corresponds to the center of the receptive field, is fixed. And the negative gain, whatever is around, changes in time. Whereas in the fatigue model, only the positive piece is varying in time. This positive piece depends on time, whereas the negative part is fixed. Okay? In the learning model, the negative component, the negative inputs from amacrine cells, depend on time as a function of coactivity of these two cells in this memory-like mechanism. Okay. Whereas in the fatigue model, the positive input from bipolar cells are vary in time just as a function of the whole activity of the bipolar cell. Okay. Now, this is only a cartoon of the model. For those of you who are more mathematically inclined, the model has nonlinearities, it has noise, and so on. But those are all kind of details for the sissies. And you can predict a number of things from these models. You can calculate how the retina will adapt to change of shape in the incoming input, and calculates all kinds of fine things. And you can also have some predictions that will distinguish the two models, what you couldn't do if you're just using words. So let me show you one such prediction and then I'll conclude. So the prediction goes as follows. You would do an experiment like this. You would look at a uniform background of light for a while, say 10, 20 seconds. Then you look at vertical bars for a while, okay? And then you suddenly switch to horizontal bars. Very similar to what I showed you before, okay? Now, in both models, the retina is saying, something new has happened when you switch things. It's sending this kind of novelty detection message to the brain, okay? And in between, it's kind of getting bored and getting tired. But the difference is that the two models, the two mechanisms, the learning mechanism and the fatigue mechanism, are weighing novelty in a different way. So in the learning mechanism, it judges more important that you're going from vertical to horizontal because this jump is larger than this jump. Whereas in the fatigue model, it thinks that it's more important that you're going from background to vertical rather than vertical to horizontal because this jump is smaller than that one. Okay? And that's a very qualitative prediction of the models that you could just go and do this experiment. This experiment is actually very doable. It hasn't been done, but I'm showing you here a very similar experiment that has been done with slightly different patterns of light and that shows similar results, and it's done in the salamander, which is a favorite for the retina. Okay? So before concluding, I just want to make a few broader comments about this, about such a plot. What this means is that when you show a shape to the retina, it gets bored of this shape. So the response it sends to the brain gets smaller. Now note that the amount of light here and here are the same. So it's really responding to a shape. And by the same token, when you show something new, it sends a very strong message to the brain. Now this is it's a very ubiquitous phenomenon in the nervous system. It's true for smell. It's true for noise. For example, if you're in an airplane, after a while you don't hear the noise of the airplane. However, you hear the crying of the baby. Okay, you hear something new happening. Okay, so and it's interesting that one should be able to get that close to the mechanism in such a simple system as the retina. And then one can think of going to more complicated system like other senses or more complicated cognitive functions because this kind of general phenomenology, maybe in a different form, is probably also true in higher functions. Okay, we're much better, we're more surprised by something new than by something old. Okay, and the second comment I would like to do, well, and also you could within the retina you could say, well, how complicated a shape can I pick up on? Okay, if here I had put my face and your face, would I still get accustomed to it already in the retina? Okay, and some of this you can start saying from the models. Okay, now broader comment I want to do make about this before concluding is the following: that you might say, well, this phenomenon is very interesting and it's true throughout the brain, but who cares about mechanisms? Well, I care. And I think it's extremely interesting to think that maybe something that is acting for memory is also acting within vision. But it's not only interesting, I think it's also fruitful because once you've identified a mechanism, you can go and start to think whether a similar mechanism is applying somewhere else, like for smell or hearing or even higher functions. Okay. So let me conclude by just a few possible lessons that one could derive from on the contribution of theory to understanding the brain. First of all, as I mentioned, these new tools like these microelectrode arrays to pick up on the retina allow you to get very, very fine data. Okay? And fine phenomena require refined thinking. So they require some fine enough way of thinking that is given to you by mathematics. Okay? Second of all, and maybe most importantly, theory points you to things to measure. Biological systems, and the brain in particular, is just too complicated for you to just go and measure something. You need some indication. So theory acts like a zoom for what to measure, like a lens. And this is where Nefertiti comes in. I've learned from the book of Jean-Pierre, actually, that the first people to realize that the brain is responsible for a number of things are the Egyptians. And they realized that if you take a convict or somebody and you destroy half its brain, well, it will be paralyzed. Half his body will be paralyzed. So they established a link between the brain and the body. Okay. Now, what you do in modern biology is very similar. Most experiments are done by destroying something and seeing what goes wrong. However, you don't destroy half the brain, you destroy a type of cell or a gene or something like this. So theory is pointing you to what to destroy. And this is why I've mentioned Egyptians and Nefertiti. Actually, the document, if I remember, Jean-Pierre, from your book, the document that describes this is just a few hundred years, couple hundred years before Nefertiti, if I remember correctly. Anyways, but, you know, why Bocuse? Well, because I think, to me, the theory helps to distinguish details, biological details, from principles of computation, as I tried to show in showing you these models. And to me, the entry of mathematics into biology is a little bit like the transition from traditional French cuisine to the nouvelle cuisine in the 60s and 70s. Because in traditional cuisine, you had typified recipes like such and such type of grain should go with such and such type of oil, whereas nouvelle cuisine comes up with general principles of computation, like greenery should go with fat. And this is how Michel Guérard came up with his salade gourmande, which is made out of beans with foie gras. Some greenery should go with some fat. This is a principle of computation and not a detailed recipe. And similarly, theory helps you to go from statements such as such and such cell does such and such detailed thing to statements such as, well, maybe a modulation of inhibition or coactivity of cells help you adapt to shapes. Okay. And finally, I think that theory helps you give substance to analogies by identifying mechanisms that you might go and look for in a broader context. Now, this is a song of praise for theory and mathematics, and maybe I should be a little bit more modest and say I still think that most insights until today come from biologists. And as we know, biologists are some kind of sublimated cooks, and one learns a lot from people who know how to cook. So I'll leave you with this quote from Brillat-Savarin, which is a very nice description of adaptation, only it occurs in not.
And we have a 20-minute discussion period. So, questions?
Est-ce que c'est fait sur des coupes?
Tiens, attends.
Are your experiments done on slice or in vivo?
First of all, it's not my experiment.
No,
this is
the one you tried to modelize.
So the experiment of Boris.
The one you mentioned.
Yeah, so the experiment of Boris and Philippe is done on cerebellum slices.
Yes.
And now the group is of course aware that slices may be not completely faithful to the real brain, so they are in vivo recording being done by Clément, Léna.
Because there is, in fact, a big difference between slice and in vivo. In addition to simply the fact that one is the whole brain, is that there are a lot of inputs which are being eliminated in the slice preparation, and the question whether they are really silent synapses was something which I wonder.
Okay, so here in the anatomy, I think it's the input are really coming from the parallel fiber. I think
yes.
So
you cut the parallel fibers?
No, so the idea is that you stimulate the granules. It's a double patch experiment. So yes. you stimulate the granule cell and you measure the depolarization in the Purkinje cell. So the experiment is just anatomically it is known that people have done electron microscopy. So when a parallel fiber crosses a Purkinje cell, basically there is a 50% chance to have a synapse. So, of course, this is taken into account. And then in the remaining 50%, what Boris and Philippe found is that they didn't see any response. So of course, there could be artifacts, or they tried to eliminate artifacts, and so actually we just believe them, and when they say that they have done carefully the experiment and that they see all these silent synapses. And actually now there are different kind of experiments where people do freeze fracture on synapse and count directly the number of receptors. And so this seems to correlate with it.
Yeah.
I have a question of understanding to the last speaker. And that was, I mean, you explained why theory is needed to do certain kinds of experiment, but I would like you to summarize once more what the content of the theory is that you used. It seems to me that you were talking about certain hypotheses. Is this what you call a theory, or is a theory more than a hypothesis? It wasn't completely clear, and where it comes from is it didn't seem to be clear whether it actually comes from physics or whether you actually meant by theory a mathematical function. The second question was if you could elaborate on Maturana's model of perception and whether it is possible that the retina will still acquire more functions than the ones you described with this last result from Harvard.
Okay. Okay, are you ready for another 30-minute talk? Yeah. First question first. You can think of. Okay, let me backtrack a little bit and say when we try to understand something, that's the way I like to summarize things is to say that you can understand means one of three things. Either you can say answer to the question what, you can answer to the question how, and you can answer to the question why. So what is the anatomy, what is the biophysical properties? How is what are the mechanisms? And why are there broad principles, like you don't want to use too much energy, you don't want to get tired, you want to do things efficiently. Okay? So in this case, so the contribution of most of the physics input is in the region of the how. It's trying to identify mechanisms. Some amount in the what, because you need to do statistical things to understand, say, anatomy, and some amount in the why, because you can try to postulate some broad principles. Now, in this specific case, what you're trying to do in terms of the structure of the theory goes as follows. You're identifying a phenomenon, which is your retina gets bored to incoming shapes and detects novelty. Okay? And you would like to understand how it works. So you would like to understand the how. So what you do is you identify some plausible mechanisms, and I've shown you two mechanisms. And these mechanisms, you could say, are not purely physics, they're not purely biology, they're both. They're something that you know occurs in biology, like the strengthening of synapses. But they're also physics because you're in the back of your mind, you have the idea that this general abstract mechanisms can be of help. Then the theory consists in taking this mechanism, putting it in a mathematical shape, and from that mathematical shape derive consequences for the function of the whole retina or of a cell in the retina. So the theory is actually the relation between those mechanisms to the prediction on how the retina will behave. And that uses mathematics. Okay. Now,
One calls that a model.
well, okay. If I like a model, I call it a theory. Now the second question, about the retina. I can't tell you about the specific reference you were making because I don't know it. However, one thing I can tell you is that if you compare retinae of amphibians, for example, or reptilians and retinae of mammals, you see big differences, and you have a tendency toward complexification. Okay. And you see some of the lateral inhibition that I've shown here, some of these center surround things in the retinae of very simple organisms, but it's at a much simpler level. You have kind of big units, and they have these lateral inhibition. Whereas in the case of mammals, you have this lateral inhibition at many layers in the retina and that fulfill all kinds of purposes. And in the mammal retina, you can see a number of things that you don't see in more primitive organisms. For example, they are much faster. In primitive organisms, the retina works much more slowly. Okay. So I'll give you one example that I know the mammal retina does, and I'm not quite sure about amphibian or reptilian retinae. I may be wrong though. But for example, the mammalian retina can predict things. When you play tennis, you're hitting the ball before you see the ball. It's just too fast. And the retina is already sending a message to the brain saying in a few milliseconds, in a few fractions of seconds, the ball will be there. And I don't think the amphibian retina can do this, although I would have to check. So I don't see why, as we evolve, the retina there could not be more of a transfer from the brain to the retina, but the brain will also continue to be better.
I wanted to ask... It works. Yeah, fine. It's okay? I wanted to ask Jean-Pierre to comment a little further on his idea of a minimal consciousness that on the slide showed the minimal consciousness for newborns, and also suggested that it could be similar for mice or rats.
Yes.
So is this kind of an idea that there's kind of a recapitulation in the old sense of ontogeny recapitulating phylogeny, that there may be a stage in consciousness that is similar to what's found in more primitive organisms?
Thank you very much for asking this question. I think we have to define more closely what minimal consciousness is indeed. I think your question is very relevant. At least there is a state of wakefulness compared to sleep and paradoxical sleep, and also, as mentioned, about attention, which is something very important in the states, within the state of wakefulness. And I think these are features which seem to be common to nearly all mammals, if not vertebrates, even birds you may find them. So whether the newborn is identical to the mouse, it's a question which actually is a very difficult one, because first of all there are few experiments done on newborns, not enough, while there are many on mice, and it seems that the newborn, and I had a discussion on this specific issue recently, in the newborn there are more features than there are in the mouse. So the mouse is even simpler than the newborn, and there are already social interactions in the newborn which are taking place, which are not taking place in the mouse. So the newborn is perhaps already more complex in his level of organization than the mouse. So I think it's already something quite interesting to try to modelize the states of wakefulness, attention, and access to some kind of integrative space, which would be minimally represented in the case of the mouse. So that's the reason I think it's useful to do these modelings, and also to use the mouse as a model. But there are, of course, plenty of limitations. And just to compare with the modelings which were shown before, I think there is no antagonism between the approaches, but it's clear that we are working at a scale which is necessarily quite different from the one of simple networks. But it's already, I think, interesting to have properties of local circuits, as it has been said, in the cerebellum and in the retina, to approach more global mechanisms which include these circuits at a lower level of integration. So that's where we are.
Yeah, I have a question.
Yes.
So
to me?
Yes.
Oh, thank you.
I have a question to you. So you showed this model of this centrally connected
global workspace.
Workspace. So my question is this: suppose that we do finer and finer experiments, and we find that there are 2 or 3 systems that act like this, or many that are anatomically distinct and that have different biophysical properties or different functional properties, which of them will be the
I don't understand. You want to say that there are several in parallels?
Right. So suppose
but this is not our notion. Our notion is that there is a unified
right, but suppose that I can distinguish different ones with different statistics in the anatomy or different functions that are active in different contexts and so on. Are there more constraints for you to say which will be the global workspace, or will they all be the global, or will their collection will be the global workspace?
First of all, you have not specified your scheme, and I think I could give an answer if you were more specific in what you said, because it's a purely formal question. Now, the fact is that there is, in an organism, one decision which is taken by the mouse to go in that direction or another one.
Right.
And this is what we want to explain, or to account for.
Right.
So if there are sub-networks which are involved, they have to be dealt with by one network which unifies the other ones. That's the way I would see the thing.
So your idea is really that there's a top network, and there's only one of them.
I think this is too simple. It's not necessarily a top level. I think there is a unified network where the global decision is being taken. That's the point of the modeling. But and I see the implication of your question. Sometimes is discussed by some theoreticists, which is, I think, a very relevant question, whether when you have a psychological decision which is taken, whether it goes always through the same pathways or whether there might be vicariant pathways where giving the final outcome. Right. And our views do not exclude this second possibility,
okay.
I want to say. But, we are at a stage which is extremely fruste, I would say in French.
Sure.
Very crude. And of course, this may not satisfy the psychologists who feels that neuroscience are not necessary, and would not satisfy the physiologists who have to get very accurate models which deal with the spiking and the synaptic transmission of neurons in a network. So, if I may say, we are in between, which is, of course, a very dangerous position to take, but at least it's a way to approach some processes which up to now were not scientifically approaches, if I may say.
Mm-hmm. I have a question for Professor Changeux regarding your experiment for the blind card, the blind world, the masked world.
You can say in French?
No, it's okay. You show us that it was a sequence in time between the card you show. You show some card with a very short space of time.
Yes.
And when you put blank cards...
Yes. This is a masking experiment.
The masking experiment.
Yes.
And does the time between the card change between the person? I mean,
I think
all the person in this room will answer the same...
First of all, these kind of experiments, as I said, were done by Stanislas Dehaene, not by ourselves. We are at the Pasteur Institute mostly working on mice, not on human beings for timing, but modeling I'm doing with Stanislas, include both, of course. The first thing which is very important is that the timing relationship are crucial in these kind of experiments. And if you have timing relationship which are being modified, then you change the outcome of the experiment. Mm-hmm. And the masking experiment is closely linked to the duration of the time of exposure of the stimulus and the relation between the stimulus and blanks or mask. And that's something which is extremely important to understand. And these timings are due to circuits which may related to those you saw in the former talks. where you have, for instance, timing of processing at the level of primary and secondary visual areas, for instance. And in particular, I did not go into the detail, and I was pleased to see that, the relationship between inhibitory pathways and the excitatory ones. And in particular, the experiment on the blink, and the model I did not show because it's published, but you can look at it if you wish. You have precisely an account of the contribution of inhibitory neurons to excitatory neurons in the processing, and this is exactly through the lateral inhibition that you prevent access to some of the stimuli according to our modeling, into the workspace. So these delays are due to time of computation and propagation in circuits. So you saw that the timing relationship are in the 10 to 100 millisecond time scale. This is the timing relationship. And I was interested by the fact that in our experiment you have timing relationship much longer ones, which means that they are really very slow processes which are taking place in the retina, which were unexpected until now, and which usually were thought to take place into higher brain organizations. But here, the psychological times are, let's say, between 50 and 200 milliseconds. These are the time scale where these processes are being dealt with. So it means that they are not that complex circuits. To enter the workspace, you may have, let's say, 2-3 relays or 4, something like this, not that many. Now, whether there is individual variability in this respect, of course, it may exist. I don't think it's very big. It's just, I think the sodium channels have the same properties, and the propagation speed is about the same. So I would not make a big difference. But what Rava mentioned, which is extremely interesting for those concerned by higher network processing, is whether the processing is for a given performance. Let's say I give the same response, behavioral response, whether each time is exactly the same network which is being mobilized. It may be not. And from an individual to another individual, for higher processors, again, you may have a dramatic variability between individuals. And this is linked in particular to two things: the epigenetic process, and many years ago with Antoine Danchin and Philippe Courage, we built up a theorem according to which the same input-output relationship can be reached through different pathways in a network, which I think we call that a theorem of variability, which is, I think, is fundamental in a deterministic kind of network to understand. So this is something. And also, there are strategies, cognitive strategies, which may be used by individuals, which may differ from one individual to another, in addition to the epigenetic process. So this is something which is very interesting to look at, because usually doing brain imaging, people average the image, and now there is more and more tendency to use a single case, single individuals, and perhaps even to separate strategies which may not be the same. So you have to realize that the processes might be quite different when you look at microcircuits like those which were presented by my two neighbors here. And when you go to a larger scale processing in the brain, you may have new type of processes taking place, and perhaps even new principles of processing.
Maybe just a little comment to add on what Jean-Pierre is saying just quickly, is that if you look at, that might amuse you, that if you look at places in the brain that are responsible for more basic functions, which is typically the back of the brain, you find circuits that are much more ordered. and it becomes increasingly disorderly and random looking as you go in the front of the brain, which is responsible for more complicated processing and cognitive functions. So as a result...
random, I would argue about it.
Well, I mean, it's not very well known.
Less understood, yes.
Well, less understood, but also probably more random. And partly because if you destroy the back of the brain, you die. But if you destroy the front of the brain, you can remake it.
The back of the brain, you die?
Yeah, you become blind. Let's say if you destroy V1, you become blind. But if you destroy the front of the brain...
There is a big difference being blind.
Why don't you let me finish my compliment of your compliment, and then you can compliment on my compliment.
I survive, huh?
So, as a result, if you're a minister and you're deciding on complicated things of what you're going to do with your country, you use much more disorderly parts of your brain than if you're a violinist and are doing automatic movements.
I think there is a question here.
Okay. I had a follow-up question on the global versus local. I think the global versus local and the higher or lower and the micro-macro are not exactly necessarily the same classifications and the same distinctions. And I apologize if I make you repeat something you already said, but the relationship between global and local is of interest in many disciplines. For example, in the social sciences, you can have global networks, if you wish, and global processing. That's completely decoupled from local processing.
No, not at all.
And the question was, to you, what sorts of relationships between the global and the, whatever you called it, the local or the lower level, what are all the sorts of relationships you have considered before coming up with a particular...
Yes. No, I think your issue is an extremely important one. And I gave a seminar in a group of social scientists who are now considering that even the global phenomena, they have been investigated at the social level, should be re-examined now on the basis of what is known on brain sciences. And there is a very interesting link to try to establish between precisely the what you call the local and the global. And you are not in a position anymore now to say that you can have a global which is entirely autonomous and can be investigated without knowing the local. Just as a simple evidence what just was discussed, the reaction times individuals at the social level are determined by the processing being done locally at the individual and brain levels. The time scale. You know, the time scale of a population of brain is not the time scale of a population of computers. So you have constraints. This is just one evident one, constraints which are imposed by this. Another aspect which is also extremely important in the social science is the so-called mentalities and change in mentalities. Are people going to change their belief in God or in whatever in 5 minutes, 1 year, or 30 years, for instance? This is the issue of religious beliefs and so on and so forth. And what is clear is that the time scale which is taking place there is not something which is totally independent from the brain. It's constrained by the brain. And the fact is that when you have stored symbolic systems in the brain, it's like learning a language, as Paul Ricoeur was saying, or learning how to write and read. And it takes generation to change. And even if you don't change the environment, it will persist and be stable for thousands of years. So the constraint imposed by the long-term memory processes, learning mechanisms, and so on, by the brains at the local level is extremely important to understand these global ones. And from the workspace story, of course, this is something more explicit and which could be measured maybe on slice, even though I am not sure, because then you are looking at long-range connection and you may lose them precisely in a slice, or at least cut them and separate them from others. But the hope is that precisely we would be in a position to identify the states of activities which are linked with global processing and local processing. This is a very well-defined prediction of the model. And even the firing patterns which are taking place in the workspace, according to these views, would be different from those you record in the processors. This is a prediction of the model. So it's a way to test whether it's right or not, or wrong.
I just wanted to make a brief comment about the previous exchange that
yes.
we hear, since this is appropriate, since this is a meeting about physics and biology,
yes.
where a physicist or where a biologist says we don't know, a physicist says random.
Yeah.
That's a cultural.
Not quite.
No. Let me give my position on this, even if I differ from what Tra said. First of all, the physiology in primary and secondary visual areas have been studied extensively for decades, for many years now, since the pioneering work of Steve Kufler, and of course Hubel and Wiesel, who have really gave a very faithful description of the response to visual stimuli and so on, and also their evolution through development. And unfortunately, the electrophysiology of the prefrontal cortex and all these association areas is much less known, and it's extremely difficult to approach their physiology because you don't have stimuli which are simple and where you can find a response. I think Rizzolatti, for instance, has been approaching this issue, looking at very large movements, like taking a nut and putting it in the mouth. And when you record in the premotor cortex, you find single neurons which respond to these extremely elaborate and complex gestures. And my view is that they look, but I'll let my neighbor respond to that. My view is that this is largely a terra incognita, and that the very difficult way to approach them from, let's say, the stimuli point of view and the behavioral point of view is such that the things look not so well defined. In fact, they are extremely well defined, and the issue which is raised by the question, and I may say here at this stage I don't have a real answer, is whether or not the prefrontal cortex, where these long-range neurons, axon neurons, are present, but also in other association areas, if I may say, whether they are not organized as highly as the secondary visual areas, for instance, and might be even a parcellization of the prefrontal cortex and a specialization for some high order kind of behaviors which are taking place in human beings almost exclusively. This is a question I am answering. And what is your reaction to that?
Well, I don't know, Vincent also probably has some comments, but I think there's one thing that probably Jean-Pierre and I will agree upon, is that neither of us knows how the frontal cortex is made up. In detail at least. And I think nobody really knows. I've asked many people. Now, I think it's much more difficult to understand what designed means than what random means. Because if you think about it, what really you mean by design is that if you compare it to random things, there are systematic biases. Okay? But then what is difficult in this is what ensemble of random things you want to compare it to. Okay? And so there's not a real sharp distinction between designed and random, because you can take more and more constrained ensembles that you would still call random. All right? And so I think to really say what does the front of the brain looks like or how random it is, what you would want to do is to say how statistically constrained it is. What are the statistical rules? Now, this has not been done until now. At least I don't know, and I've asked a number of people, and I don't know. I don't think this study, and it's a very difficult study, very extensive experimentally, of course. Now, the reason I said it's random, and the reason I still think there's a measure of randomness to it, first is that certainly there's no way there's enough coding space in the genes for you to say you attach neuron 1 to neuron 2, neuron 3 to neuron 4, and so on, and you go until neuron 10 billionth. So certainly the rules must be some kind of statistical rule. And when I said there's some amount of randomness, is again because you said there is more randomness than in V1. Yeah. V2. Well, I think it's still true, because what happens is that I said V1 now. Jean-Pierre is promoting me to V2, but if you destroy V1, as I said, you become blind. So typically, if you have in humans, but not if in the dog, not okay, maybe, but if you destroy Jean-Pierre's dog's V1, he doesn't become blind. But in humans, okay, if you destroy, but if you destroy the front, you remodel. If you destroy on the left, you'll pick up from the right-hand side. So it's as if you're taking a car, you're cutting it in half, and you can still drive it, and nobody notices. So if it were very, very designed in detail, this would be very improbable.
If I may just say one thing, which is extremely interesting, is to agree, because I am.
You agree with me?
To some extent, yes, to some extent. But is the notion of variability, as it was discussed at the beginning, of the brain phenotype, and I think the whole issue of variability, which again, to my opinion, is linked to the mechanism of epigenesis of the brain circuits during development. I think it's an issue which has to be investigated by all means, and that's perhaps a common conclusion that we would agree on.
One more question, and then we should stop. So I just.
I have a very general question, actually. It's a general question for all of you, particularly because I don't come from a theoretical background. So what I know from the experimental biology, like in what appears in theory, we look at a simple mechanism first, or even only protein or simple thing, and then we test it or look at it in the whole environment. And the examples you've given us, particularly the last speakers, from theoretical approach, was a simplification of a phenomenon, sometimes only looking at one cell, not even taking into account the time. So how does theoretical physics or approaches will face bigger complexity, networks with more cells, with the different characteristics, and taking this into account, taking into account different areas with different properties?
I may just say one thing before my two neighbors polish their answer and they will conclude. It's clear that if we really want to do the neuroscience of the future for higher brain function, we will have to deal with enormous population of nerve cells. And I don't think that any kind of intuitive scheme, non-quantitative scheme, will work. And as I think the two speakers said, and this I think was, to my opinion, a very interesting conclusion, is that even simple circuits have features that you cannot predict just looking at them, from a pure intuitive way, and having a mathematical model for predicting their properties is an extremely useful move. Now, whether it's theoretical physics, mathematics, or computer science, to my opinion, doesn't have any interest. It's just making computation for the neuroscience. And if we have now brain imaging, which is going to take place at the cell level, and have individual neurons being recorded with a whole brain, you can imagine how difficult will be the computation from single events into billions or even hundreds of billions of neurons. And I think the problem of computation of brain states at the single cell level will be an enormous task. So I don't think in the future we may do neuroscience without having these computation. Now, whether it has to do with theoretical physics, I don't like the word, because it means that these are statistical physics mechanisms and models and so on, but that we need mathematical treatment, certainly yes.
Okay, on this.
We should close.
Well, why don't we have? We will give 2 quick answers.
Yes.
Go ahead.
Quick.
Okay, so first of all, I can say that probably the place where it's most involved is the hippocampus, where people record very different kind of cells, and so they have different pattern. And so, yes, probably the thing will be to record many cells and to assemble the whole network, given specific connectivity patterns and things like that. But I can also conclude with a story. Is that 25 years ago, Jean-Pierre gave a seminar at École Normale in the physics department, gave a very nice introduction to the acetylcholine receptor. But I was a young physicist, so okay, I saw that the acetylcholine receptor was very interesting for the brain, and in fact, Jean-Pierre was saying, okay, we're going to understand the brain with the acetylcholine receptor. So I was very naive, and I said, okay, this is fine, but okay, what you have a Turing machine, the concept for what is consciousness. And I remember very well Jean-Pierre telling me, wow, this is the typical physicist question. Of course, this is completely non-scientific.
I say yes, and I confirm what I said, because at that time it was. And
so I'm happy that we have switched places somehow.
So just
a last brief comment.
Okay, just a quick answer. So I'm very grateful for this question, not only for the question, but because of the person from whom it comes. But it's good that you asked, because I forgot to mention it. A quick answer is the following: that I think you would like to know what happens in the real environment for an assembly of cells with all the complication put in. But what I've learned from Israeli theoretical neuroscientist Chaim Sompolinsky is that it's very useful often to bring the system to the extreme of what it can do. And that's what we try to do. We show, instead of showing a natural movie, which is very complicated, you show bars of light. So you push the system to the limit of what you can do to uncover its properties. And this is similar to the risk of being ridiculous in front of social scientists. This is a bit similar of the idea of Foucault of looking at crazy people to understand normal people. You go to the limit, and then you try